Bismillahirrahmanirrahim. Assalamualaikum, brothers and sisters. Today's lesson on standing wave on a string highlights the use of partial derivatives in determining the transversal velocity and acceleration of a particle in a string as a function of time. So join me till the end of this video. Watch and learn. And here's the question. For a standing wave on a string, the distance between nodes is 0.125 meters. The frequency is 256 hertz, and the amplitude is 1.40 times 10 raised to the negative 3 meter. What are, letter A, the speed of waves on this string? Letter B, the maximum transverse velocity at an antinode. In question letter C, what is the maximum transverse acceleration at an antinode? As shown in the figure, okay, we have the representation of the shape of the string at two different instants. Notice that both ends of the string are fixed, and so they are at rest, and the midpoint between them is also at rest or at the equilibrium position. We label these particles or points as the nodes, capital N. These are points at which the string never moved. That the points at which the amplitude of string motion is greatest are called the antinodes, and they are labeled here as capital A. In this problem, we are given the distance between the two adjacent nodes, lambda over 2, equal to 0.225 meter. So that means that the wavelength lambda is equal to 0.450 meter. In addition, we are also given the frequency of the wave, small f, equal to 256 hertz. Likewise, we are also given the amplitude, capital A of the wave, equal to 1.40 times 10 raised to the negative 3 meter. Our target variables are, in part A, the speed, small letter v, of the wave on the string. In part B, the maximum transverse velocity, denoted by small letter v's of y max. It is understood that the transverse velocity of a particle is at the antinode. And in part C, the maximum transverse acceleration, h of y max, and maximum transverse acceleration is also at an antinode. Moving on to our computations, in part A, we determine the speed v of the wave, which is simply equal to uh, the wavelength lambda times the frequency f. That is, s- speed v is equal to 0.450 meters multiplied by the frequency 256 hertz, which can also be written as 256 per second. So when we do our math, we get the speed v of the wave equal to 115 meters per second in three significant figures. At this point, we also uh, determine the angular frequency denoted by the Greek letter, small Greek letter omega, which is equal to twice the product of pi and the frequency f, or multiplying 2 by the value of pi and the frequency 256 per second, we get this value for the angular frequency omega equal to 1.61 times 10 to the third power radian per second, also rounded to three significant figures. Likewise, we also compute for what we call the wave number, small letter k, which is equal to the angular frequency omega divided by the speed of the wave v, or the wave number small letter k is equal to 1.61 times 10 raised to the third power radian per second divided by the speed v, 115 meters per second. So again, when we do our math, we get the value of the wave number k equal to 14.0 radian per meter, also in three significant figures. In part B, we calculate for the transverse velocity v sub y max at an antinode. It is just equal to the angular frequency omega times the wave amplitude capital A. Question is, how did we arrive at this simple equation? Well, one of the objectives in this video lesson is to highlight the importance of mathematical derivation. All right. Uh, the derivation of this equation b sub y max equals omega times a, as well as that of the transverse acceleration a sub y max equals omega squared times the amplitude a, discussed, all right, later in part C. All right. First, we consider the equation of the displacement uh, or y displacement function with respect to the position x and the time t. All right. So the equation is y is equal to capital A times sine kx multiplied by sine omega t. Right? So we can express this displacement function equation, if you're going to substitute, okay, the given what we call quantities, that is the displacement y, all right, with respect to x and t is equal to 1.40 times 10 raised to the negative 3 meters. This is the amplitude, all right, of the wave, okay, multiplied by the sine of the value of k, which is 14.0 radian per meter. Okay, x is considered our variable, and that is multiplied also by sine of omega t, where the value of omega computed earlier is 1.61 times 10 to the third power radian per second, and t is another variable, the time t. All right, we call this the displacement y function equation. Now, from the given displacement y function, a times sine kx multiplied by sine omega t, all right, we determine the transverse velocity, Vy, by getting the first partial derivative of the y function. That is, b sub y, okay, with respect to the time t is equal to, all right, the first partial derivative, all right, um, of the y function with respect to the time t. So this symbol represents the partial derivative of the displacement y. And this symbol is a curly small letter d, right? This is read as the first partial derivative of the y function with respect to the time t, right? And the y function, of course, is given as uh, the amplitude, capital A, multiplied by sine kx, k multiplied by sine omega t. So we determine the transverse velocity By by getting the first partial derivative of the y function, okay, with respect to the time t. At the same time, we ignore the x variable as if it is a fixed number, right? And in differentiating um, sine omega t, okay, uh, we need what we call the chain rule, right? The term containing the x variable, a sine kx, is treated as a constant. So we just write it here as is, and then get the what we call partial derivative of sine omega t. And in doing so, uh, we apply one rule in partial derivative. We call it the chain rule, all right, which says that the first partial derivative of sine omega t is equal to cosine omega t, all right, multiplied by uh, the partial derivative of omega t, which is equal to omega. So we arrive at this simplified equation for the transverse velocity By with respect to the time t equals capital A multiplied by omega uh, times sine kx and multiplied by cosine omega t. Okay? So, uh, from this equation, okay, we can deduce that uh, the transverse velocity Vy is considered maximum if both sine kx and cosine omega t are at their maximum values of 1, okay, positive or negative 1. All right. So from the preceding derivation of By max, all right, we came up with this equation, right? By max at an antinode is just equal to omega times uh, the amplitude A, or angular frequency omega times the amplitude of the wave. So substituting, all right, into this equation, uh, the values for omega and capital A, we get By max equal to 1.61 times 10 to the third power radian per second times 1.40 times 10 raised to the negative 3 power meter. So doing our math, we get the value of the transverse velocity or By max equal to 2.25 meters per second rounded to 3 significant figures. And following the same mathematical derivation for the transverse acceleration, right? Uh, we could have determined the value of the transverse acceleration a sub y with respect to the time t by getting the second partial derivative of uh, the displacement y function. But what we have here is getting the what we call first partial derivative of the velocity function By, right? So By has this equation, capital A times omega times sine kx multiplied by cosine omega t. Again, we consider or treat, all right, the variable x as a constant, okay, treating it as if it is just uh, a number, all right? That's why we just bring it down here as a omega sine kx. But in getting the um, first partial derivative of cosine omega t, again, we apply the chain rule. That is, the derivative of cosine omega t is just equal to negative sine omega t times the derivative of omega t, which is equal to omega. Hence, we arrive at this desired expression or equation for the transverse acceleration ay with respect to the time t. That is negative capital A omega times sine kx multiplied by sine omega t, where again, the maximum value of the transverse acceleration ay occurs if both sine kx and sine omega t are at their maximum values of 1. So we can now proceed in getting the answer to the question in part C. That is, the maximum transverse acceleration at an antinode is just equal to the product of the square of the angular frequency omega and the amplitude of the wave. That is, a sub y max is equal to 1.61 times 10 to the third power radian per second. Okay, we square this and then multiply it by 1.40 times 10 to the negative 3 meters. So, doing your math, we get 2.59 times 10 to the 6th power radian squared per second squared. This is the result of getting the square of omega. So we again multiply that by 1.40 times 10 to the negative 3 meter, which is the value of the amplitude. Hence, we get the final magnitude of the transverse acceleration, right? AY max equal to 3.63 times 10 to the third power meter per second squared, rounded to 3 significant figures. So that's it. We are done. Let me say mabuhay. Till the next episode. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.